We're going to be looking at a p-n junction structure. It's simplified. And then we're going to go over this question right here. So we have two metal contacts on both sides, and we have an anode and a cathode. On the anode side, we have a p-type silicon, P for positive, n-type silicons, N for negative. The p-type is created by adding acceptor atoms. The n-type is created by adding, this should be donor, not donut atoms, and N is our equal to negative. When p-type silicon is brought into contact with our n-type silicon, a p-n junction is formed, and this is often referred to as a semiconductor diode. If a positive voltage is applied to our p-type side with respect to our n-type side, the diode is going to turn on. So if we have some voltage going to the p-type, and our current will flow, right, with respect to the n-type. Now, if a negative voltage is applied to the p-type side with respect to our n-type side, the diode remains off and zero current flows. So we're only going to have current flow through this battery if we have some positive voltage through the p-type. The p side is called the anode and the n is the cathode. So let's look at the p-n junction depletion region, because that's really what this question is asking us here. So we have a diagram that looks like this. We have our ID and I of S, which we're not going to be focusing on, but just note the directions, they're opposing each other. We have holes on our p-type, and we have ends, which are the negative, the electrons, on our free electron side, which are the right. So we have holes and free electrons. And in the middle of them is our depletion region, where the energy goes from our negative, the electrons, into the holes. And then we also have our little diagram right here, a little chart. We have potential versus x-axis, so we have a barrier voltage V output. So when a p-type Si is brought into contact with n-type Si, the holes diffuse from the p side to our n side. So we have holes in the p, and they're going to want to go to our n. And electrons diffuse from the n side to the p side also. So the free electrons want to go into the left, where the holes are, and the holes want to go to the right, where the free electrons are. This is going to cause our depletion region, and this is going to be formed around our junction. The junction is the area, and the area around the junction is depleted of free holes and electrons. So we are not going to have any free holes and electrons, we just have our bound charges. The donors and acceptors near the junction are ionized, and they leave behind uncovered bound charges. So plus on the n side and negative on the p side. So we're switching them because they want to go into the other side. The separation of charge creates an electric field which opposes further diffusion, and a barrier voltage, and it must be overcome. This is what our barrier voltage is talking about here. Again, the barrier voltage is the separation of charge, and this is going to create our electric field, which is this E, and it's going to oppose further diffusion. And we're going to have to overcome this barrier voltage to keep transferring electrons. So this can be like a battery charged to 100%. Electrons want to diffuse from the n side to the p side because there are not many on the p side, and for the same reason the holes want to move from the p side to our n side. They want to kind of swap. The separation of charge always creates an electric field, and this is going to oppose our further diffusion. Again, separation of charge always creates an electric field. We're going to start on the positive charge and end on the negative charge. The voltage is equal to our electric field strength times the distance. So voltage is the E times our X. So let's actually look at this question now. Which of the following is true for the depletion region surrounding our p-n junction? First, it says in the depletion region there is zero electric field, and that is false. We have our electric field right here. The separation of charge always creates an electric field, so it's not going to be A. Next, we have in the depletion region, the amount of charge stored stays constant as the bias is varied. Well, the amount of charge stored in our depletion region, there's not going to be anything really stored because we want to keep moving them back and forth from the n side to the p side. So this is not going to be true either. Next, we have in the depletion region, there are free electrons in holes, which cause a separation of charge. Now, this is not what causes the separation of charge. Remember, the separation of charge creates an electric field. And in the depletion region, there's not free electrons and holes. The reason why there's electrons and holes here is because they want to move across to the other side. So this is not going to be true. They're not free. They're moving. We see right here that a depletion region to be formed around the junction is the area around the junction, depleted of free holes and electrons. In the depletion region, there are almost no immobile ions. Well, this one's also going to be false. The donors and acceptors near a junction are ionized, and they leave behind uncovered bound charges. So we have, again, our pluses on the N and negatives on the P. So if they are ionized around our junction, and we know that ionization, we have immobile ions, it means that we are going to have some immobile ions around here. So in the depletion region, there are immobile ions. So this is also false, meaning that the correct answer for this one is actually none of them. And that is just going over our PN junction in the depletion region.